Hello Math 1093, this is Dr. P with Sines of Progress. So our goal in this video is going to be to graph this function right here, f of t equals 3 sine of 2t minus pi over 2 all minus 1. And I'm going to do this using a couple of different approaches, one using transformations and another one using what we know about the amplitude, midline, period, and phase shift of a trig function. Okay, but I want to start with a transformational approach just as a way of illustrating how we can put this whole thing together just by making a few moves. So I've put a grid here that has trigonometric coordinates on both axes. In other words, I've got nice little multiples of pi on the horizontal axis, which is my t-axis, and I've got integer coordinates on the vertical axis. All right, so let's start by graphing the simplest function that we can think of that would be related to this, which is the function sine of t. All right, hopefully by now you know that sine of t has a point at the origin. It meets the t-axis again at pi and meets again at 2 pi, and that's one complete cycle. Also, the maximum value is 1, which occurs at pi over 2. The minimum value is -1, which occurs at 3 pi over 2. Also, the graph is symmetric about the origin, meaning that the other side is going to look the same except upside down. Let me draw the curve and then I'll explain what's meant by that. All right, so we draw the curve. There we go. Usually when I have you draw one of these, I'm going to ask you to draw at least 2 full periods, which is pretty much what I've done here. You see there's 2 full periods there. Okay, now what do I mean, by the way, by symmetric about the origin? What that means is if I were to rotate the entire graph by 180 degrees, it would look exactly the same as if I hadn't done a thing. Okay, so if I can rotate the entire graph by 180 degrees around the origin, and that'll preserve the shape and position and everything. Okay, so that's the graph of sine of t. Now I'm going to throw down another trigonometric grid, and we're going to graph another function. So we'll put in this one. There we go. Move it over. All right, so this time I want to graph a different function. That different function is going to be, let's do 3 sine of t. I'm just going to do this one transformation at a time now. All right, so what does 3 sine of t look like? Well, again, my t-axis over here. This time, I'm going to take the original graph, which is over here, and I'm going to stretch it by a factor of 3, because if I take my entire function, multiply it by 3, I get a vertical stretch by a factor of 3. So this time, I'm going to have the same t-intercepts, multiples of pi, but this time my maximum and minimum values are going to be 3 and -3, respectively. So now my wave is going to look a lot taller. And it should look a little bit wavy. It shouldn't look like sharp triangle shapes. It's just hard to draw with a pen. Come on, go through there. There we go. All right, hopefully if you're using pencil and paper, yours will look a little bit better than mine. Okay, but that's the idea anyway. Okay, so now I've taken the original graph and stretched it by a factor of 3. All right, now let's make another modification. So I'm going to come over here, give myself a bit more room to work, and then, let's see, throw down another grid. Okay, this time I'm going to graph the function 3 sine of t minus 1. Okay, how is that connected to the previous one? Well, I'm just taking the previous function and subtracting 1. Hopefully by now we know that that is a vertical shift by 1 downward. So this is my t-axis. This time at t equals 0, I'm going to be at -1 because I'm just looking at what's happening with this graph, and I'm going to put every key point 1 unit lower than it was before. So instead of having a maximum at 3, I'm going to have a maximum at 2 here. And I'm going to be back to -1, and then my minimum is going to be at -4, and then I'm back to -1 again. All right, and I'll just keep propagating these points back, and pretty soon I should be able to draw a nice little wave. Same wave as before, just a unit lower. Okay, yeah, you really have no idea how hard this can be with a tablet. I'm actually drawing on a tablet that doesn't have the screen on it. So the tablet's separate from the place where all the stuff is showing up. That's why things are a little bit off sometimes. Okay, so that's my new wave. Now what about all this business going on inside of the argument of the sine function? Okay, I'm just going to copy this over. So I have this over here and can look at it. F of t equals 3 sine of 2t minus pi over 2 minus 1. All right, so moving on over, I'm going to put down another grid. You may be wondering how many more of these are we going to do? Not too many more, I promise. Okay, let's talk now about the function 3 sine of 2t minus 1. So you notice I've replaced t with 2t. What does that do? In one of the previous videos, I talked about how doing that will cause a horizontal compression by a factor of 1/2. So now I got to think about what all these points, all these key points are going to do if I compress them horizontally by a factor of 1/2. Well, let's see. So I'm still going to have a point at 0, -1 because compressing that doesn't move it anywhere. But what about this point at t equals pi over 2? Well, if I compress that by a factor of 1/2, I now have a point at t equals pi over 4 and still at a height of 2. And then my next key point is going to be at pi over 2. My next key point is going to be at 3/4 of pi, and I'll have another one at pi. And I'm just going to write or draw a few more points here, a few more key points just for illustration's sake. There we go. And then a few on backwards here. Okay, this is a little bit tedious, but bear with me. And draw the wave. Ooh, it's just like a pin slalom here. Back and forth and back and forth. Okay. Missed a spot. And then we'll go backwards. Anyway, picture's a little cartoonish, I know, but hopefully you see that this is a compression horizontally by a factor of 1/2. Okay, one more, and then I promise we're done with this approach, and we'll do one other approach, which is a little bit faster. Okay, I'm going to put down one more grid here. Move that over. Okay, so now how do I get the function 3 sine of 2t minus pi over 2 minus 1? You might think that this is a horizontal shift by pi over 2. That would not be quite correct, because what I'm doing here in moving from this function over to this function, I'm not replacing t with t minus pi over 2. I'm actually replacing t with something else. And to see what that something else is, I need to write this in a different form. I need to factor this 2 and get t minus, and then think, what do I get if I factor 2 out of pi over 2? I get pi over 4. And that means that actually the phase shift or horizontal shift going on here is pi over 4, not pi over 2. So that's something to keep in mind, is when you see this form here, there's actually a little bit more that you need to do in order to see the correct phase shift. You need to factor that coefficient of t out, and then see what this would look like if we were to replace t with something. We're replacing t with t minus pi over 4, actually. All right, so I think I'm about ready to start drawing here. So everything's going to move over pi over 4 units to the right. So this time, my the sort of center point here is going to move over to pi over 4. And then I'm going to bounce up and down, just going to do everything pi over 4 units later. And I'm going to go ahead and draw that, just for the gratification of it. Eek. There we go. And then what do I have back here? I've got another minimum, another midline point, another maximum, and so on. I'm not going to draw quite as much as I did before, because hopefully this gives the idea. But just to make really clear, because there's a lot of symmetry and regularity in this wave, just to be really clear, this point here, that point that used to be sort of the origin of my wave, even though it wasn't at the origin in the coordinate plane, that point has now moved over here. So the transformation is a movement by pi over 4 units to the right. Okay, so we've been doing this for 9 minutes, and we managed to graph one graph. But hey, it's a good graph. It's a very nice graph. But what if we want to do this faster? So the key is to use what we know about attributes of trig functions. So I'm going to put one more grid down here, and we're going to do this in one swing. So suppose I want to graph this function. I'm going to use everything I know about this form here. First thing I'm going to do is I'm going to rewrite it in the form I did earlier, which is f of t equals 3 sine of 2 t minus pi over 4 minus 1. That factorization step is important. It allows me to see clearly what the phase shift is. It lets me get it in the form f of t equals a sine of k t minus c plus b. So now it's just a matter of figuring out what all these parameters are. So let's see, the midline, as you might have guessed, is y equals -1. I'm not going to put an equal sign, let's put a colon there. The amplitude is the absolute value of 3, which is just 3. The period is, what is that? That's 2 pi over k, that's 2 pi over 2, this number, which comes out to pi. And then the phase shift is this value right here. Not pi over 2, but pi over 4. And if I have these 4 bits of information, oh, and I need to check whether there's any reflection going on. We sort of did that informally earlier. But there's no vertical reflection going on here. No vertical reflection because this parameter here is a +3, not a -3. All right, so given these 5 bits of information, I can draw the perfect sine wave to represent this function. So how's that going to work? So what this phase shift means, actually let's first draw the midline. The midline is at -1, and that's helpful to have around. Midline is y equals -1. Okay, now, the phase shift is pi over 4. So because this is a sine function, it sort of starts on the midline. The cosine function starts at a maximum or minimum, but the sine function starts on a midline. Just to illustrate why, that's because this earlier function that we drew, the very first sine function we drew, what's happening at the origin? We're on the midline there. We're in the middle. So moving on back. Oh, everything is moved. This is gross. Okay, thankfully my little red line in the graph did not move. I don't know why. I don't know why it does that. Anyway, the phase shift was pi over 4. Boy, that really drifted over. Sorry about that. Okay, so that means that t equals pi over 4. I'm going to be on the midline, and that's going to be the starting point I use to draw my graph. Okay, what else do I need to know? I know the amplitude is 3, and I know the period is just pi. So after pi more units, so after this much, I don't know if you can see me drawing in the picture there, after that much, I will have completed one full period. So that's the distance between this point and this point. Okay, so between those 2 points, I'm going to have another point where the wave crosses the midline, and I'm going to have one maximum and one minimum. The maximum will occur exactly halfway between these 2 points, and because my amplitude is 3, it'll be 3 units up. The minimum will occur between these 2 points, those second and third ones there, this point and this point, halfway between those, and because my amplitude's 3, it'll be 3 units down. And that will create one full cycle of this function. And if I want more cycles, I just sort of continue the process. I draw another period, so that'll be between here and here, and then cut that in half. So these are the 3 midline points here. Draw another maximum and another minimum. And then draw the wave. Okay, let's just compare and make sure that those two look exactly the same. Oh, would you look at that? I drew a little bit more over here on the right, but you will notice that this graph here on top does exactly the same as this graph here on the bottom. If I were to continue this to the left, which I'll do for just a little bit, I would get exactly the same function. Okay, so those are 2 strategies. One is to do transformations bit by bit, and the other strategy is to use what we know about transformed trigonometric functions. Let's get that all in one frame there. Again, sorry about the mess with little rectangles moving, but hopefully that gives you a couple of techniques for thinking about graphing of trig functions. I know that was a long video, but I hope worth it.